Students, we're going to do a couple of example problems doing rotational kinematics and uh, doing translation between the rotational and translational variables. So, hopefully you've seen the last video where we talked about the particular, you have the uh, translational variables, your x and v and t, and then you have your angular variables and the conversions between those. And so we're going to try to do kinematics problems. So let's start with some rotating objects. So in my house, I have a fan, right? So fan blades. Um, Something like that. And it's rotating around. So there's one other thing I haven't mentioned is that when you see things in real life and they're talking about the rate at which they rotate, you'll often see something like this thing is going to rotate at 300 revolutions per minute. Right. So let's say it starts out with this. So this is our initial velocity. And what we're going to do is let it come to a stop. So omega final is 0. We're going to let it come to a stop in 10 seconds. That seems reasonable for a box fan, I guess. And so we want to figure out the acceleration. Right? And we'd like to figure out the number of rotations. So here's what we're going to do. First off, we need to make sure we have understandings of our units here. Is when we do a problem, so the word rotation is synonymous with revolution. So, and one revolution is 2 pi radians. And this is the thing, is that when we're doing problems in rotation, so one is our units are always something like theta is going to be in radians. And then angular velocity is going to be radians per second. And then angular acceleration is going to be radians per second squared. Now, we're never going to use degrees here. So, we're always going to try to state things in radians, and you know that 2 pi radians is 360 degrees. So, 1 is our units. We're always going to go with radians. And 2, we're always going to leave the calculator in degrees. Anytime we need to make a conversion, we're going to do it manually. Now, there's a reason for this, is that if you go in and try to calculate stuff, we're trying to switch between tangential or translational and rotational variables. It's just easier to always leave it in degrees and do the translation by yourself. Right, so we're always going to use these units. And then the other thing that we'll do is convert radians per second to revolutions per minute. We'll often do something like that. So we have a revolution per minute is, well, there's 2 pi radians per revolution, and there is 60 seconds per minute. So that should be 1 minute over 60 seconds. So we're going to be very careful how we, actually I had it right the first time around, times 60 seconds per minute. No, I don't have that right. We're always going to do this conversion, and so 1 rev per minute is, well, 1 rev is 2 pi radians over 60 seconds. All right, so we're always going to have a unit conversion between those things. Okay, anyway, so we have our units here, and so that means we can do some conversions on this. 300 revolutions per minute times, well, 1 revolution is 2 pi radians, and we'll have our minute, 1 minute is 60 seconds. So we'll do 300 divided by 60 is 5, and then 5 times 2 pi is 10 pi radians per second. And often I'll leave it in terms of 10 pi, and then I'll put in pi at the very last minute. Oftentimes it'll come out okay like this. Or this is also 31.4 rad per second. Okay. So you can do it either way. Oftentimes when I do problems, it'll be nice multiples of pi, and so I'll leave it like that till the end. So now we're going to organize this based on what we've already done for kinematics. We're going to do the same sort of organization. So our angle theta is something we want to figure out. The number of rotations is theta is something. Our angular initial velocity is 31.4 radians per second. Our final, because it's going to come to rest, is 0. Our acceleration is something we want, and our time is going to be 10 seconds. So given this stuff, our first part, the accelerations, well, we can go and say that's, we know the velocities and the time. Our acceleration should be the change in angular velocity with respect to time. And so it goes from 31.4 to 0, so we'll have 0 minus 31.4 radians per second over 10 seconds, and that is 3.14 radians per second squared. And I'm running out of space here, but the other bit we need is our angle theta. And what we can do there, let me get another sheet of paper here, just off to the side, is we can go and say, well, given that we have now these 3 things, we can say that our angle is going to be our average velocity times our time. Well, this is going to be 1/2 0 plus 31.4 radians per second times our time is 10 seconds. I'm running out of space here. And so we'll have 31.4 times 5. We pull in the calculator because I'm lazy. 31.4 times 10 divided by 2 is 157 radians. And then we go and we look and we say, oh, we're specifically wanting to know the number of rotations times 1 rotation is 2 pi radians. And so theta is, we're going to divide by 2 and divide by pi, and we get 24.99 rotations. 25 rotations. There's obviously rounding going on because I use pi. So that is a reasonably straightforward way of attacking one of these problems. And so this is a good stopping point, but this is part 1 of a video. What I'm going to do is go the long way around with this problem. I'm going to draw this out again. I'm going to show you another way of attacking the problem.